Right, sulfur. Now, seems to be a bit of a legacy from syllabuses gone by. We don't really do a lot of sulfur chemistry anymore, probably because most things associated with it are quite poisonous. It's a pretty good reason, no? Sulfur forms S8 rings. So it's actually with a valency of 2, it forms two single covalent bonds with its partners and they form a ring of 8 sulfur molecules. 8 sulfur atoms, sorry, to make a sulfur molecule, an S8 ring. And it forms these wonderful yellow crystals. You can see the shiny faces on the crystals. There are two versions of sulfur in the solid form, two typical versions. Now we've seen this before, haven't we? We've seen when there's two different types of an element in the solid form. What was the name given to that? We saw it with carbon. Remember? With graphite and diamond. What were they called? Just different arrangements of the atoms, in this case of the molecules within the structure. They're called allotropes. Allotropes. Now, you need to do a little bit of investigation here. So I want you to look at your textbook and make notes about the following things. Okay, so extraction. Where do we get sulfur from and what part of the world? Now, we get sulfur from underground sulfur beds. It actually forms, it comes in minerals also, but it forms in layers under the ground. And places where it's found in abundance are the United States, Mexico, Poland, and Sicily. And it's also found in metal ores like zinc blende and in natural gas. Okay? So there's some places around the world where it's really, there's lots of it. It's in beds under the ground. You can get it from minerals like zinc blende and from natural gas. What's it used for? Have a look in your textbook. What do we use sulfur for? It's used, most of it is used for making sulfuric acid, which is a very useful acid. Very cheap and very useful. It's used in lots of different processes. And sulfur is also used in the process of making rubber tires. And it makes the rubber more flexible, but it also makes it tougher. This is called vulcanizing the rubber. And it's used in making dyes for colouring cloth and different things. Just a little picture here to show you what happens in the process of vulcanization. So you've got your natural rubber molecules, and what happens is the sulfur forms bridges between these polymers, these long molecules. It forms a bridge, and that makes it flexible still, but it's elastic and it's more tough. It's tougher. Have a look at that video about how sulfur is extracted. I think it's called the Frasch process. It's quite an old process. It's a really quite instructional video. How is sulfur dioxide made? Well, we take our sulfur and we burn it in oxygen. So here we have sulfur on a small spoon. This is called a deflagrating spoon. We have sulfur on a spoon within an atmosphere of oxygen, and it burns with a beautiful blue flame to make sulfur dioxide. It makes this colourless, pungent, toxic and acidic gas. It's a nasty gas, sulfur dioxide. We can also get sulfur dioxide, we saw in the last section on metals, when we roast metal ores in air, some of the less reactive metals like copper and zinc. So zinc blende, when we roast it in air, we can produce sulfur dioxide. Okay. What's sulfur dioxide used for? Well, its properties are quite interesting. It will bleach wood pulp in the process of making paper. So you make the wood pulp, which is a kind of grey brown color. You make it white, and also you can use it for bleaching some natural fibers, for example, silk and wool. It can make them white instead of using a stronger bleaching agent which could damage the fibers. Okay, so sulfur dioxide is used to bleach wood pulp in making paper and for preserving food. If you put a small amount in the packaging and in drinks, just a small amount, it kills bacteria and it stops bacteria from thriving, from developing within the food. A classic place to put them is to put sulfur dioxide is in plastic containers that contain dried fruits, and so it's a sealed container and it stops the dried fruits from going off over time. This is sulfur dioxide. 1 sulfur, 2 oxygens. Now, like we said, sulfur and sulfur dioxide go to make sulfuric acid in what's called the contact process. And this process, I think it's called the contact process. It's something to do with the contact between the gases and the catalyst, which we'll talk about in a second. I think that's where it got its name. So, the raw materials for the process are air, which we've got plenty of, water, which we've also got plenty of, and sulfur or sulfur dioxide. Now, if we've got sulfur, then obviously we have to burn it with air to make sulfur dioxide to start with. Okay, so we make our sulfur dioxide, or we get sulfur dioxide from somewhere else, and then we mix that sulfur dioxide with more air, more oxygen, and we pass it over a catalyst of vanadium 5 oxide. Look at the temperature, 450 degrees C, just like the Haber process. And this is a reversible reaction to produce sulfur trioxide. And that sulfur trioxide, if we spray down concentrated sulfuric acid, it turns into oleum. That oleum comes out of this container, is mixed carefully with water, and you get concentrated sulfuric acid back. You get much more back than you put in. So obviously there's a net output. Okay. The conditions you must remember, 450 degrees C, that's 450, not minus 450. Pressure is just above atmospheric pressure to make the gases flow through the system, and the catalyst is vanadium 5 oxide. Vanadium 5 oxide is V2O5. V2O5, just so you know. Right, let's have a look at an overview of the whole process. So we're making sulfur dioxide, then sulfur trioxide, and converting that into sulfuric acid. So we start with sulfur, we burn it in air to get sulfur dioxide. That sulfur dioxide is mixed with more air, passed over the beds of catalyst, pellets of catalyst obviously, so you've got a good surface area, 450 degrees C, and in this reversible reaction, you make sulfur trioxide. This is actually an exothermic process in the forward reaction, like the Haber process. So you make some sulfur trioxide, you dissolve that in concentrated sulfuric acid to make this, and this is our funny named oleum, okay, sometimes called fuming sulfur trioxide. And then we mix that with large quantities of water, so we don't get any explosions, to produce concentrated sulfuric acid. Okay, that's the process you need to know. Some points about the process. Now, Le Chatelier's principle. The forward reaction is exothermic, so a low temperature would give a higher yield, but that would give a low reaction rate, a slow reaction rate. So we use a moderate temperature to give a reasonable reaction rate, which is a compromise temperature. The catalyst increases the rate of reaction. One of the things to bear in mind is that at a very low temperature, catalysts might not be very efficient. So this temperature is also good for the catalyst. The 450 degrees helps the catalyst to do its job. It's an optimum operating temperature for the catalyst. Sulfur trioxide is constant remove from the system, so it forces the equilibrium to the right. High pressure would favour the production of sulfur trioxide, but it's only 3 moles producing 2 moles in this case, and it's not really necessary. Any unreacted gases, unreacted gases are recycled, and it's dangerous to add sulfur trioxide to water directly, so oleum is made instead. It's explosive if you add it directly. The uses of sulfuric acid, so you can see it here. 30% are used to make fertilizers, 15% to make detergents, paints and pigments, fibers, plastics, and then other uses. That's a battery, isn't it? So fertilizers, paints and dyes and fibers, making salts and detergents, and then car batteries. Car batteries is down here. It's got an electrolyte of sulfuric acid. You need to remember some of these. Properties of sulfuric acid. Now, so when it's dilute, sulfuric acid behaves like a strong acid. It's dilute, but it's a strong acid, so it fully dissociates, and it does everything that acids do. There's some reactions that we saw in section 8. Acid plus base, insoluble base in this case, acid plus insoluble base, acid plus alkali. You'd also get acid plus metal, wouldn't you? Acid plus carbonate. It does all of those things. When it's concentrated, sulfuric acid is desperate to attract water, and it's a good dehydrating agent. So if I mix it with sugar, with glucose or sucrose or whatever. So with sugar, what it does is it rips the water out of the sugar, leaving just carbon. And that carbon comes out of a beaker like this, kind of spectacular form. And all of this is just carbon. It's like charcoal. And you see lots of vapor, water vapor comes off because it gets very hot. It's an exothermic process. So what do you see? You'd see water vapor. You can write this down. You see water vapor, steam. You smell, it smells of caramel. It smells of caramel because of the sugar getting very hot, heating up. And you see this enormous black gunge of carbon. With hydrated copper 2 sulfate, which has got obviously water in it, that's its water of crystallization, concentrated sulfuric acid causes that water to be ripped out of the crystals. So you can see as we put it on top of the copper sulfate here, the crystals start to go white. So when it loses its water of crystallization, the copper 2 sulfate becomes anhydrous and it turns white. Okay, you can put that in your observations there. It goes from blue to white. You can also use sulfuric acid, concentrated sulfuric acid, to dry gases. So if you've got a gas that's got water in it, it's a damp gas that's been produced, and you want a pure and dry gas, if you bubble it through sulfuric acid, damp gas in, as long as the gas doesn't react with sulfuric acid, of course. This wouldn't work, for example, with ammonia, would it? But if it's not very soluble and it's got some water vapor in it, then you put the damp gas in here and the dry gas comes out the top. Okay, have a look at the pages indicated and answer any questions.